Yeah, welcome. So today we want to talk a bit about Flink's past, its present, and bright future. Let's get started with the past. So everything started in 2014 when a couple of PhD students and master students were looking for a job. Instead of applying like traditionally at some companies, they decided to continue working on what they were doing all the time, working on a research project called Stratosphere. The idea was to continue open sourcing this project, building a community around it, and make a living from it. So what better place is there than the Apache Software Foundation to do exactly that? So in 2014, the Stratosphere project was donated to the Apache Software Foundation, and Stratosphere, now under the name of Apache Flink, entered the incubator. Back in the days, Apache Flink was solely batch processing, but batch processing on streaming data flow runtime, which already supported things like long-running operators and streaming shuffles, for example. And this should become quite useful later on, as we will see. For the historians among us, the first Apache Flink release happened in August 2014 and was the version 0.6. So everything started with batch processing. However, we didn't have to wait long until Flink learned how to stream. With Apache Flink 0.7, the community released the first version of the DataStream API. The DataStream API is a second API next to the dataset API on top of the same runtime. In its initial version, you could already do continuous processing of real-time data, consuming from Kafka and Flume, for example. It had support for tumbling and sliding windows. Even the first version of session windows were there. And you could do streaming joins, for example. Interestingly, the DataStream API, or enabling streaming, didn't require to add any substantial new features to the runtime. The DataStream API simply exposed what was already there. So in November 2014, Flink learned to stream, and you could do continuous processing of real-time data, which enabled the first set of simpler streaming applications. Next came the introduction of the state API with Flink 0.9. With that, a new wave of applications was enabled, applications which were stateful and could remember things. As of today, the majority, if not all, production Flink applications, so applications which are in production, use state. So this underlines the importance of this feature. Keeping state around in an operator is not the true difficulty. You could also do this before Flink 0.9. However, it becomes tricky in case of faults. And faults, especially for long-running jobs or applications and in a distributed setting, are more the rule than the exception. So Flink has to properly handle them. If you have a stateless job, recovery is easy. You simply restart the operator and let it continue processing. However, when you have state, you not only need to restart the subtask, but you also need to reinitialize the state. You basically have to remember where you left off and from where to continue in order to produce correct results. And that was actually the true novelty of the 0.9 release. It introduced the asynchronous barrier snapshotting algorithm, a variant of the Shandy-Lamport algorithm, to create a globally consistent snapshot in an asynchronous manner. And by having these snapshots, it was now possible to also recover from failures by simply resuming from them. And this feature enabled for the first time to build exactly once processing pipelines with Apache Flink. So the next evolution of stream processing was that it became stateful and gave you exactly once processing guarantees. Due to the nice properties of the asynchronous barrier snapshotting algorithm, Flink could also do away with a prevailing belief of this time that stream processors could not give you both low latency and high throughput, so to say that they were mutually exclusive. But due to the fact that the checkpointing algorithm has no blocking points, so the checkpointing operation itself happens asynchronously, it has no effect on the latency. Moreover, since you have the checkpoints, you don't have to persist the intermediate streams, which means your throughput is not limited by disk I/O, for example. That way, Flink can achieve throughputs of tens of millions of events per second and can go down to latencies down to 1 millisecond. That way, Flink proved that you can actually have low latency as well as high throughput in a modern stream processor. Another important addition was the support for event time, which came with Flink 0.10 in November 2015. Event time effectively allows you to handle events in the order they actually happened, and not in the order they arrived at your stream processor. Take, for example, the series of Star Wars movies. If you watched them in the order they were released in cinema, you would probably leave the cinema a bit confused because the story has some breaks in it. However, if you watch them in the order they intended to happen, like starting with episode 1 and then watching them in an increasing order, all of a sudden the story makes sense. And that is basically the same for stream processing, where you have streams where the events are out of order. So with event time, you can actually you can now guarantee computational correctness because you can process unordered streams properly, because now the delays or the out of orderness can be corrected or can be treated correctly. Moreover, there's no longer a difference whether you process data in real time or process the same data which you have stored somewhere later on in form of a batch job when using event time. They will both give you the same results. So in November 2015, the community completed the most important set of streaming features, which already enabled a wide set of different streaming applications. The next major step was the introduction of the process function in February 2017 with Flink 1.2. With that, Flink proved that it's more than analytics, because the process function, which is conceptually located below the DataStream API, gives you access to state and time on an event basis. So unlike the DataStream API, which uses streams as an abstraction, you can actually implement data-driven applications using the process function. There are many different use cases which are very interesting using the process function, but one I would like to mention is I guess you already heard about it, but it's a really cool application. DriveTribe. It's a company which built a complete social network on top of Flink using exactly this function, which is quite impressive. So with the introduction of the process function, Flink evolved into a platform which can not only do batch and stream processing, but also develop data-driven applications and execute data-driven applications. All right, so much for the past. Now let's take a look at the present and Flink's future. In the past year, we have seen, which I consider as the present, a huge surge in Flink's adoption. And due to that, the Flink community spent a lot of effort hardening and scaling existing features. It improved Flink's interoperability and worked hard to make Stream SQL production ready. Now let's take a look at some of these features a bit more in detail. One of the most game-changing additions feature-wise was the support for incremental snapshots, which came with Flink 1.3. The idea of incremental snapshots is that you don't have to always snapshot the whole state, but it's enough to snapshot the difference with respect to the previous snapshot. And by replaying the sequence of incremental snapshots, you can recover the state completely in case of a failover. By only storing the difference, the diff, you can dramatically decrease the size of snapshots and thus also the time it takes to create the checkpoint. And that way, this feature unbottled the next wave of Flink applications which need to treat extremely large state, like state which has a size of terabytes, for example. Another important aspect of Flink is its failover behavior, especially how fast it can recover from faults. With Flink 1.5, a local recovery was added. Local recovery keeps a copy of the snapshot locally on the task manager. That way, we can now almost instantaneously recover from task failures by simply rescheduling the tasks to its previous location. This, of course, only works as long as there's no node failure. In order to also tolerate node failures, we intend, or there are ideas to replicate the state across multiple task managers, such that a new task manager can take over for the one which lived on the failed node. Moreover, another idea to speed up recovery from failures is to use persistent volumes, which can keep your snapshots and can be remounted to newly spawned machines. Another problem we try to tackle is the problem of varying workloads. And this actually applies to all Flink applications. So in all real-world use cases, you face changing workloads due to daily cycles, weekly cycles, due to some seasonal spikes or unplanned events, for example. With a fixed set of allocated resources, you will always run eventually into the situation that you are over or under provisioning. In case of over provisioning, you're basically wasting CPU cycles, which could be used for something else, and consequently, you're wasting money. When you're under provisioning, which is even a bit worse, then you cannot keep up with your SLAs, make your customers unhappy because the service quality degrades, and they leave your they will leave you basically. So ideally, what you want to have is a system which adapts the resources with respect to the actual workload. And that is something we addressed with Flink 1.5, where we reworked Flink's distributed architecture. And now with the new architecture in place, Flink supports full resource elasticity and allows you to manually adapt the parallelism of a running job. Moreover, we integrated, we changed the way the client and cluster communicates. Now it uses REST. It's REST-based, which much better integrates with container environments. What else is happening on the deployment front? Well, you have seen that with the introduction of the process function, you're now able to develop data-driven applications. However, when you deploy or start these applications, you still have to deal with a cluster. So first you have to deploy a cluster before you submit the application to it. And this makes the operations quite difficult. So what we want to do is we want to make applications a first-class citizen of Apache Flink. The goal is to make deploying Flink applications as easy as starting a simple process on the operating, like simply starting a process. The idea how to achieve this is to bundle the application code together with Flink and a bit of extra logic into an image, which you can then start in a container. When you start this container, the container process will automatically connect with the other started application processes, and they will figure out automatically which role to take in order to execute the job distributedly, or the application. So one of the processes will become the job manager, and the others the task manager to execute the job. That way, we want to improve operations and effectively remove the cluster out of the equation. A first step toward this direction is the introduction of a new operation mode. If you take a look at the spectrum of Flink applications, you see that they have different requirements in terms of control over its resources. So if you have a batch job usually consists of multiple stages of short living stages, where each stage has different resource requirements. In order to efficiently execute this batch job, Flink needs to be in control of its resources to allocate and release resources. In contrast to that, real-time applications or data-driven applications, which are long-running applications, are usually constrained by external systems from which they read and into which they produce. They're constrained by SLAs. And it's easier to reason about the required resources from a holistic view. So an external system releasing and starting new resources can do this better. And in this case, Flink simply needs to react to the available resources. So in order to support this, these type of applications better, we want to add a new reactive mode. So what we already have in Flink is what we now call the active mode. In the active mode, Flink is aware of the underlying cluster framework and can talk to it. At the moment, this works for Yarn and Mesos. But in the future, we also want to add it for Kubernetes. There are no fundamental problems which could prevent that. In contrast to that, the reactive mode is oblivious to its underlying runtime environment. And an external system starts, for example, a new task manager, which will then register at the Flink cluster. And Flink, in this mode, the Flink cluster will react to the newly available slots and scale the job automatically up or down. If you want to learn more about this, there's a dedicated talk later today by Gary Yao at 4:10 p.m. at the Maschinenhaus, I think. Last but not least, a bit related to that is you've seen that you can, or I told you that you can now manually scale Flink applications up and down. We actually want to automate this. The idea here is that we introduce a rescaling policy, which you assign to an operator, which can trigger or tell the framework, well, look, this operator needs to scale up or down. Depending on this, on the implementation of the rescaling policy, it could make this decision based on the current latency, throughput. You could define some thresholds for the resource consumption, or even react to external systems or connector signals to make this happen. This is something the community is currently looking into, and will hopefully complete this feature soon. All right, with that, I will hand over to Aljoscha, who will tell you a bit more what happened on the Streamng SQL side. Thank you.
Thank you. Thank you, Till. So we have seen how Flink evolved to allow new kinds of applications by adding new APIs, how it became more powerful in dealing with state, and how it had new primitives for deployment. But one thing has stayed pretty much constant in Flink, and that is that we use Java if we want to write Flink jobs. So that is not hard, that's not a problem, because most processing systems, they require Java, but it's a bit of a blocker for adoption for a wider audience. So for example, data scientists, data analysts, they don't necessarily want to program Java. That's why the Flink community in 2015 with Flink 09 started adding support for a relational API. So this started with the table API, and then with Flink 1.1 in August 2016, we added the first version of a SQL API to Flink. So this had support for event time processing. You could use the same SQL for stream and batch processing. It has support for user-defined functions. But up until recently, there was still some plumbing required that you had to write in Java. So for setting up the sources and sinks of your pipeline and for starting the execution, you had to write some Java code. But this changed recently with Flink 1.6, which was released a couple of weeks ago, with the addition of what we called a unified table sources and sinks, where you can define sources and sinks in a YAML file and use them in the SQL client that was introduced in Flink 1.5 to write SQL programs without writing any Java code. So this is, maybe some people don't know about this, but for me this is quite the milestone, because up until then you always had to write Java, and that's why I quickly wanted to demo this. So I have done a little screencast with a Docker Compose-based demo setup that we have for demos and for the training. So I'm starting all the components. Then I'm starting the SQL client. I did prepare some sources and sinks in advance. So now I'm listing the tables that I have available, so the sources. I only have one, which is some artificial source of taxi ride events. I'm looking at the schema, which is also defined in YAML. And then I do a query right there in the client, which will send it to a Flink cluster for execution, but will show the results right there in the client as they stream in. Right. That's for the SQL client. Another interesting thing in the SQL world to do is joins. And there's one type of join that we call enrichment join. So in this example, consider we have a stream of trades, so buy and sell orders, and we have another stream that gives us currency conversion rate updates, and we want to enrich those trades with the correct currency rate at the time at which that trade happens. So the naive way that some systems support is just to keep a table in your join operator, say, of the latest currency rate, and then when a trade comes in, you enrich the trade with that currency rate and emit the result downstream. This is easy to do, but it has some problems with out-of-order data and event time, where you want to make sure that you join a trade with the most recent currency rate at the timestamp at which that trade happens, but not with a currency rate that happened at a point in the future seen from that trade. And in SQL, so in batch SQL, you can express this with a correlated subquery, which is kind of hard to do. So in Flink, the community is working on a join called time version table joins, where in addition to just the currency rate, we also keep the current currency rate, we keep the past currency rate and the time at which they occurred, and then we can join the trades with the correct currency rate that is the most recent one at the time that the trade happened, but not a newer one. Staying with SQL, let's look at an example. Say we have a taxi company or a ride-hailing app, and we get events for when rides start and when rides end, and we would like to detect some patterns in that time-based series. And I think writing a SQL query for expressing that is kind of hard, if not impossible. That's why the Flink community is working on support for match recognize. Match recognize is a recent addition to the SQL standard, which allows for specifying regex-like patterns that you can use to detect patterns in streams. And how you do that is that you specify a bunch of pattern variables. So we have this variable that checks if the event is a start event. We have a bunch of other pattern variables that specify events that also happen and have a different write ID from the event that was the start event. And then we have a pattern variable for events that have the same write ID as the start event and are an end event. And we use these in the pattern definition, and this way we can find these patterns in the stream. And we can use SQL for pre-processing the data. We can use SQL for processing the results of that, and we can use, for example, the no coding required YAML file source and sink definitions to do this without any coding required. Lastly, I want to talk about the processing landscape. So Xiaowei also talked about this quickly in yesterday's keynote. And what it looks like today is that there is batch processing system. So you have Hadoop and Spark prominently. Flink is also a powerful batch processor and will become more powerful. And you have the streaming systems, of which Flink is arguably the most powerful open source system. But Flink has this underlying execution runtime, but different APIs for the different use cases. So this leads to some headaches if you, for example, want to process historical data, use this to bootstrap state in your application, and then switch over to a streaming execution mode. That's why the community is working on providing a unified API, be that some data stream-like API or a SQL API, where the system picks the right algorithms and data structures for the task that you want to do and dynamically switches over between processing of historical data, where, for example, you can have efficient join algorithms like a hash join, where you have a build side and a probe side, and then switches over to a streaming execution mode. To conclude, we have seen that Flink has always had a powerful engine. It has added a lot of features that enabled new kinds of applications. We have added support for SQL, which widened the audience even more. And the Flink community will work on improving those things that we have. So it is focusing on more deployment options, more active integration with Kubernetes, auto-scaling. We are working on improving working with large state, for example, local recovery that Till mentioned. And we are working on improving the audience that can use SQL, that can use Flink, by improving the non-Java type APIs. So be that the recent introduction of the SQL client, the recent introduction of the unified table source interfaces and sink interfaces, be that match recognize, which is still being worked on, or new types of joins that enable new use cases. So if you are bored anytime during the conference, check out the SQL client, because that is really an easy thing to check out, where you can just, in a couple of seconds, as you saw in my demo, check out what you can do with that. So that's all for now. Enjoy the next keynote and also enjoy the rest of the conference. Thank you.